somebody in the lab, was it you that showed me or somebody showed me that I presented the binary search algorithm, the test code for binary search, that my test code was incorrect because I used an unsorted sequence of numbers. Is there a person in here right now? No? Did I do that? Does anyone? I can't seem to find the work. Or I may have done.
I know mine was fine, so. Yeah, mine was fine.
All right. Okay. All right, so what I thought we would do today would be to look at the sample exam 3 problems and just go through those and talk about them. If somebody else has a concern or an idea, please bring it up. No? So I'll create a file to store my answers, and I'm not going to go through the process here. This exam 3, by the way, this exam is on Wednesday. Yeah. So I'm not going to compile and run and develop test code. I'm going to skip that. I'm going to go through these problems as if we were taking the exam together. Okay, so I want to show you what I'm looking for as an answer. All right, here is the first problem. Write a predicate function that checks whether 2 vectors are identical. So I'm looking at this problem right here. They should, so by identical I mean they contain exactly the same elements in the same order. A declaration of the function is shown in figure 1. The function returns true if the 2 vectors are identical, otherwise it returns false. So I'm going to copy this. Actually, on the exam, you could do the following. I'll just show this to you. So this would be problem 1. So the function takes a vector A and another vector B. Is A and B, are they identical? Well, they need to have the same length, so we're going to check that first. So if A dot size doesn't equal B dot size, then return. So first we check for the same length, and if we don't return, then we're going to check each pair of values within the 2 vectors, the pair formed by the values at the same indices. So for int I, I'll use I, it's a common index variable. I is less than A dot size. We could use B dot size, but we know that they're the same thing. So if A of I doesn't equal to B of I, then we return false. They're not identical. Oh, this should be returned false. So we have to return false if they're not identical, and return true if they are identical. So what we do is we look for a mistake. So the first mistake is that they have different length. And if we don't find that mistake, then the next mistake is there's some pair at position I where A of I is not equal to B of I. If we find that mistake, if we find that point where they're not identical, then we'll return false. Now, after we check all of these facts and we don't find any problems, then we know that they're identical. So that's good enough on the exam. You don't have to copy the function declaration. You could just provide that as your answer. That's good enough on the exam. Nevertheless, in the following problems, I'm going to use the function declaration in my answers from this point on, although it's optional during the exam. So we need to implement this function is unlucky. By the way, are there any questions regarding this first solution?
Just on a certain word, what does the word predicate mean?
A predicate function
Yeah.
is a function that returns true or false.
Okay.
So a predicate is like a proposition, a statement of fact, which is either true or false. So we call this a predicate function. How about this problem 2? Implement a function that determines if the unlucky number 13 appears in a vector. The function returns true if 13 appears in the vector at least once, otherwise it returns false. So is it unlucky? So it's a little bit different than this one. If we find, we're only looking for one value. Here we're checking every value. Every value has to satisfy a criterion. Here we only need to find one value to satisfy the criterion, that the value equals 13. Once we find one, we know it's unlucky. So let's look at each value. So basically we're going to examine each value in the vector. So what do we do here?
Equals 13.
If E of I equals 13, good. And then what do we do if we find one that equals 13? Return true. It's unlucky. Oh wait, we return true, don't we? Unlucky.
Yeah.
Oh, yeah. So it is. So it is unlucky. And outside the loop, what do we do here?
Return false.
Return false. Because we checked every value, we didn't find an unlucky number, so it is not an unlucky vector. There we go. All right, number 3, write test code that tests every statement in the is unlucky function that you implemented in the previous problem. Express your tests using assertions. So we need a vector of int. We'll push back to 7. Push back an 8. That gets the lucky numbers in the Western world and the Asian world. Any other lucky numbers? I think in China the lucky number is 8. Here we would say the lucky number is 7, right? Okay, so let's have an assertion. Assert V. What do I do here?
The function.
I got to call the function.
Is unlucky.
Oh, is unlucky. And I pass in, oh, this should be a lower L here, right? And I pass in V. So this is going to be equal to what? False. Let's put a 13 in there. Now it's now unlucky. And notice I pushed another value. That's because I didn't want 13 to be in the last position, because that's a special case. Although we could test that special case. So this would be, although on the exam, I don't want you to try to create exhaustive test cases. What I want on the exam is for you to have a test code that provides good coverage in the sense that it tests every statement in the unlucky function, unlucky function. So here we should execute this return. We should come into here. That's a statement, return true. It's a substatement. And here's another statement, return false. And of course, the parent statement, this will run if its substatement runs. So you need to, at a minimum, provide test code that triggers a true and a false return value. But just doing that isn't good enough for a good test. But for the exam, that's what I'm looking for. How about this one? Problem 4. Is strictly increasing. Write a predicate function. Once again, it's a function that returns true or false, called is strictly increasing, that checks whether a vector of integers contains values that are in strictly increasing order. A declaration of the function is shown in figure 3. The function returns true if the elements are in strictly increasing order, otherwise it returns false. For example, it will return true for v equals -2, 4, 5, 6, and 8, but it will return false for 3, 4, 6, 6, and 9, because there's 2 6s, that's not strictly increasing. So we can't have two values that are equal in a strictly increasing list. All right. So think about how you would implement this. We know that this is not strictly increasing because we found a pair of neighbors that were equal. Or maybe in another example, the later neighbor is smaller, not even equal, but even smaller than the first neighbor in the pair. So we're not comparing we're not comparing this value with that slot there. We're just looking at neighbors. So we look, is -2 less than 4? Yes. Is 4 less than 5? Yes. Is 5 less than 6? Yes. Is 6 less than 8? Yes. Is 8 wait a minute, I've got nothing to compare 8 to. So I'm not even going to look at 8. So I'm going to look at pairs, 4 pairs starting at these positions, position 0, 1, 2, and 3. Or in general, position 0 through n. N here is, n means what? Number of values? what's the last position here that I have highlighted? This is position 0. This is position 1. Position 2. Position 3. So the last position that I used to form a pair is position 3. And if we say that n is the size of the vector, then we have n equals 5. The last position is 3 in a vector of length 5. So that's n minus 2. So beware the one-off demon. Call it a demon now. So we need a loop that basically looks at the pairs, and so we want to range across those indices that I just talked about that are the first index of a pair. So I is less than. I'm going to make everybody think about that again, if I can.
Be that size minus 1.
What's that?
B dot size minus 1.
Very good. Excellent. Excellent. I thought someone was going to say size minus 2. All right, you're now trained. You're ready to graduate from the class. You can get that. All right, so let's go through. So what we want to do is compare. We want to look at the pair. So it's v of I, and we want to compare it in some way to v of what?
I
I plus 1
Good, I plus 1.
is greater than or equal to.
Is v of I greater than or equal to?
Mm-hmm.
Then what do we do?
Return false.
False.
Yeah, you're thinking faster than I am. So I didn't have the idea in my head. I just had to check that you did it right, and that's what I would do. Any other?
Return true.
Yeah.
We return true after the loop. So there it is. Return true means it must be strictly increasing because we didn't find a bad pair. We find a bad pair, we return false. You missed the criterion to be strictly increasing. If we checked every pair looks good, return true. All right, the fifth one. Write a function named flatten that takes a two-dimensional array of integers with 100 rows and 200 columns and returns a vector that contains all of the array's elements. Copy the values a row at a time. In other words, first copy row 0 into the vector, then row 1, then row 2, and so on. Now here's the declaration. All right, so we need to flatten this thing. So, at the end of the day, we're going to end up returning a vector. Well, we don't have a vector to begin with, so we need to actually create that. That's an empty vector. And we'll use pushback to append values from A onto V. So we do it a row at a time. Oh. So we're going to have two for loops. And inside the middle loop, we're going to be appending. with a pushback. Pushback. And what goes there? Well, that'll be some value from A, right? Something in here. And then at the end, close these loops off, and then return V. So we can use, I was thinking we could use the variables, we just have to pick, we can use row, or we could use I. I, okay? Huh? I is shorter, isn't it? So I is less than 100, yeah. And then this one is J. J less than 200. And then we return A of I, I'm sorry, not return, we push back A of ij. There it is. All right, let's look at the next one. Findmax. Implement a function called findmax that determines the maximum value in a two-dimensional array. A declaration of the function is shown in figure 5. The variables rows and columns are constants defined elsewhere in the program. You don't need to define them, just use them. So we're going to find some maximum value. So we're going to have some variable called max. Actually, I don't know. Yeah, maybe we'll do it like that. There's two ways of doing this. We can save the position of the maximum value in the array, or we can save the value, it's a copy of the value itself. So there's two approaches. So I'll do the second approach, which is to keep a record of the maximum value that we see, not the position where the maximum value is at. So it's going to look a lot like this one. We basically have to look, we have to examine the entire array. So we'll need integers to represent the indices, and and let those integers range across all possible indices. So this is rows, and that's columns. So we're looking for the next biggest number. We talked about this problem before. We don't know where to start. You know, if we start at 0, you know, it's a bad choice. Let's correct that in a moment. So if A of ij is bigger than the max value, that the largest value we've seen so far, that's what max is. Max is the largest value we've seen so far. If the new value that we're looking at, A of ij, is bigger than the biggest value we've seen so far, then let's correct our notion of what is the biggest. So the biggest value we've seen so far is now a new value, the value at aij. Maybe this is easier to look at if I do this. I don't know. So why is this a bad choice for the variable max?
Could be a negative.
Yeah, all the values in the array could be negative, and 0 would be larger than all of them. And so we would report a value, we would report 0 as the largest value in the array, where in fact the largest value is less than 0. So a better choice is some value. It could be any value in A. I mean, it could be this value. It doesn't matter. We could, any value. The only thing is we don't know how big rows and cols are, so let's just play it safe and set it to the first one. But it has to be something from in the array. Or it could be the smallest possible integer. That's the other thing. We could also max. There's some constant in the language which probably represents the smallest possible negative integer. And we could set it to that. All right. Any questions about that one? Do you want to see the alternative implementation? The alternative would be to record the position of the maximum value and then return, it's probably not worth doing. I'm going to skip that. What about 7? To search. Implement a function that searches for a given value in a vector of integers. If the value is found, the function returns the index of the value in the vector. Otherwise, it returns -1. Do not assume the values are in order. Do not use binary search. You cannot use binary search if the values are not in order. Then there's an example. So search for a value and report its index, or return its index to the calling code. Search for a value k in V and return the position of k in V to the caller. So we need to scan through all of the indices that are valid for V. Basically, we're looking for K. If V of I is K, we found it. What do we return?
1.
Return true.
No, return 1. Return I.
Return I. Good job.
Yeah.
The position of K in V. V of I equals K. That means the position of K in V is I. It's kind of three values there to think about. And let's suppose that we don't find K. What do we do?
Return -1.
Huh?
Return -1.
Yeah, return -1. Now that has to be done after the loop finishes. So by the way, when you have a return statement inside a loop, the loop is finished. So that's another way of exiting the loop. You can return from the loop. You can also break. You can use the word break. That causes you to exit the loop. The other way to exit the loop, of course, is to is for the loop condition to become false. Then you exit the loop. There's three ways to exit a loop. Call break, call return, or have the loop condition evaluate to false. All right, what about a binary search? Search for a given value in a vector of integers whose elements are in strictly increasing order. If the value is found, the function returns the index of the value in the vector, otherwise it returns -1. So binary search. So binary search. In binary search, we have a start index. We've got an end index. And then we have a midpoint, but we're not going to compute that just yet. And we're going to keep computing the midpoint and looking for k at the midpoint. We'll move start up or end down depending on what we find at m, the midpoint. And we'll continue this as long as start is less than or equal to end. So let's compute the midpoint. The midpoint is start plus end divided by 2. So if it's an even number, we don't get any truncation. If it's an odd number, we get truncation. Once we have the midpoint, we want to look at the midpoint. So is k less than the midpoint, the value at the midpoint rather? If k is smaller than the middle, then that means we can bring the end index down. We don't need for e to be m. We can set it to 1 before m. Actually, we need to. Else, if k is greater than v of m, let's suppose k is greater than v of m. If k is bigger than the value at the midpoint, then we're going to bring the start index up to m plus 1. Else, and there's only one other possibility. That means we found k. If k is not less than v of m, it's not greater than v of m, it has to be equal to v of m. So in that case, we found it. What do we return? What's the in this case? What's the index of k in v? M. Just wanted to hear you say it with confidence. We found the m. We're searching for the index. We're searching for the position of k and v. We found it. Now let's suppose that we don't find it. Then we're going to squeeze at some point, because we're subtracting 1 here and adding 1 there, that S and E will kind of exchange positions. That eventually E will be less than S. And so when E becomes less than S, it means we've gone far enough. And we return what?
1.
Huh?
-1.
-1. Good job. Means the convention is return -1 to indicate that the index does not exist. There it is. That's a typical exam number 3 in this class. You have to be able to run through that. I always ask binary search. So that's 100% guaranteed. But I may make this a predicate function, return true or false. Or I may ask you to implement this for an array of integers rather than a vector. So there's some variations.
From b dot size to just size.
Exactly. Pretty straightforward changes. All right. So the work covered is what? Labs 3, 4, 6, and 7. But the questions that we just went through, that's what the exam looks like. On the final, it'll look more like lots of problems from all 3 exams will appear.
Wow.
So it's not got an internet problem right now. So is there anything left over from the labs that you want to talk about?
I actually have a question about binary search. Do you have to do that exact algorithm? Or
No, you can use a different one.
as long as it works.
Yeah, as long as it works.
Okay.
This is the simplest that I've seen. I used to omit this -1. You can omit that -1 there so that E is always 1 past the value you're concerned with. You can write it that way, but my experience is the code comes out messier. So I think this is the simplest formulation. Actually, over the years, I could never remember. I always wing my problems in class here, which is easy to do. They're simple. And I could always forget this little trick, and it took me many years before I finally remembered it's easier to let E be the index of the last value that you're considering. If you omit that -1 and let E be 1 past the end, the code is messier. And the reason that I was doing that, by the way, is because a lot of algorithms in the C++ data structures are based on this notion that you have an end position, an end, and this end is always 1 past the last item. And so I was applying that rule that in general, if you look at the list data structure or the vector data structure, different data structures in the C++ library, they let the concept of an end be 1 past the last valid index. And so I just naturally started to express the problem that way. But every quarter that I would teach it, I would always come up with some really kind of messy code. And then I learned from my students that it's actually better to start like this. All right. Is there anything you want to look at in the labs? Maybe talk about even the tic-tac-toe problem?
Oh, the one that's.
That's the next one. So
Yeah, can we look at that?
yeah, let me pull that up. Let me see if I can reconnect here. I'll try it one more time. It says it's good, but
We just need to hit,
Nope.
fresh.
You're dumb.
That was it. Yeah, so this final problem is to implement a tic-tac-toe game. And what I'd like to do sort of as a way to think about how to solve this problem is to implement a different game that's similar. And I think it's called 4 across or 5 across. Does anyone know that? Is it 4 across, 5 across?
Connect 4.
Yeah, Connect 4, that's it. Connect 4. So I don't even know. Oh, I see. So you have an opponent. So you play this. And you need to get 4 in a row.
Top good.
What's that?
On top.
Do that one? Yeah, I don't know a good strategy, so maybe I'll do that.
Ah.
Oh, look at
Oh, you
that! Well, what do you know? I wanted to go up through here. I thought that would be clever.
Don't put it on the third one.
Don't put it on this one, yeah. Yeah, I wouldn't know what to do here. That one? No, that's not a good one. Anyway, I don't want to do this, but
No.
we can implement this in code. And this is very similar to the tic-tac-toe problem. But, you know, we don't have time to do it today.
Aw.
But you can imagine playing tic-tac-toe. You move, then the computer moves. Then you move, then the computer moves. And what happens when you move? So the program has to wait for the player to move. The player enters in a move. Check that the move is valid. If the move is not valid, ask the player to move again. And if the move is valid, then check, okay, is the player win? No. Okay, is the game over? Yes, okay, tie. Or if it's not over, then let the computer move. And what we'll do for the computer moving, we'll just pick a random position. And so the computer moves. And then we check, does the computer win? Yes. Well, then we say the computer wins. If the computer doesn't win, then we say, well, are there any moves left? No. Then announce a tie. If there are moves left, then let the player move. And then you get a loop. See, you see the loop? So we'll sketch that out together when we, maybe in the next lecture that we have.
Do you want us to use a multi-dimensional array, or are you okay with us using a single-dimensional array or dotting it?
You can use a single dimensional array. Yeah, you can. So actually, let's start on it. It might take a while, so let's just get started on it, because and we'll stop at a natural break point, and then we'll continue later. If we wait and start later, then we won't have enough time to probably finish it.
Okay,
It's like, no, I didn't do anything.
You gotta see why it's not.
I think that's lab 8. Is that lab 8?
So we're supposed to play against this
Lab
game?
9.
Oh, lab 9. We play against the computer.
Oh, okay. I did wrong then.
Yeah, let's just get started today. And I'm going to copy.
Push one and then push two.
I'll call it main.cpp. And we'll just try this. All right, so we got the beginning there. So let's think about this. So we'll ask the player to enter a position. So it'll look something like, we'll have the player enter in a value like example, 2, 1.
That's only if you're using a multi-dimensional array.
Well, how else would you?
If you use a single dimensional and you mod it by 3, then you would have 1, 2, 3, 4, 5, 6, 7, 8, 9. If you fill the spots.
Oh yeah. We could do it like that. Do you want to do it like
So then
that?
that way you only have to enter, the player only has to enter one number. instead of
That's a
entering
great.
row
That's a
and
great
column.
idea. Let's do that. That's a very good idea. Thank you. So enter a position, and then we're going to read this, and we'll call it the like the player move. So that has to be. That's a good idea, actually. I think it's a lot easier. And basically, see, it's like a sculpture, and I'm chiseling away the marble here. I'm just gonna, there's a loop, right? There's an infinite loop. Let's just see that, how that works. You enter a position, 3, 1, 5, like that. How do I kill this? It's an infinite loop. Like I made an infinite loop there. How do I kill it? Huh? Control C. Does everyone know that? I press Control C to terminate this. All right. So, but what we want to do here is actually display, we want to display the board. Oh, actually, this is a Connect 4. We're not doing tic-tac-toe. So it's enter a column. And so we have to pick a column. So that's easier, actually, than a, So display the board. Let's just break it up into some functions. So we're going to, maybe what we'll do is print the column numbers. How many columns? Is this a standard board? It looks big to me.
That's not a board, yeah.
Huh?
That's a standard board.
There's another one?
No, it's a standard board right there.
That is.
I thought it is.
3, 4, 5, 6, 7.
Yeah.
So how do we store the information? Like here, I was just entering 3. Okay, the player chooses column 3. So how do we digest that? What do we do with that information when we read it in to this integer? What are we going to do?
Use a switch statement?
Huh?
Maybe use a switch statement.
Use a switch statement? What do we do in the switch statement?
If you enter, say, 1, then...
Wait, let me ask the question a little differently. We're going to have, like each time we make a play here, the state of the game changes. How do we represent the game state? Let's see, there's 1, 2, 3, 4, 5. There's 6 times 7, right? So 42. 42, there's 42 cells. we got to know whether a cell is empty or has a player in it or has the computer piece in it. So each cell has 3 states. So how are we going to manage that information? Use an array?
Array.
You know, vectors are easier, aren't they? Or array is not bad. Maybe an array is going to work better. Because we have to do tests. We've got to test on diagonals and rows and columns. An array might be better. Let's start with an array. So we'll need a data structure. That's called a data structure. So it's each cell in the array has 3 states. Either it's empty, the player, or the computer. So we can't use a Boolean variable for each cell. We have to use something else, like an integer. Or we could use a character value. Let's do it like that. Let's use a char. That's a 1 byte value, represents a character. And these characters will have it either be a blank, an X, or an O. And then we can just like see out the board, make it easier to display the board that way. So the board has got 7 columns and 6 rows. So 6 rows and 7 columns. I don't know if that's maybe it should be 7, 6. I'm not sure yet.
No, rows columns.
This makes more sense, right? Okay. And you know, this is not initialized, so we could initialize it like this, or initialize it down here. So let I range across the rows. Let J range across the columns. That's got to be a 7, I know. And then we're going to set board of IJ to a blank char. Now look, I'm not using. Let's try this. I want to get an error for this. Watch this. I hope it's an error. See, because the board is of type char, an array of char, and I'm trying to set it to a string. So this is actually not a character. What we need is a single quote. But let's see what kind of a error message we might get for that. Assigning to char from incompatible type constant char. Constant char 2. Anyway, it is the error message. And we need to use, this indicates a character. It's a blank character. See, there's nothing in there. Is there something in there? It's an ASCII value 32, you know, if it was an ASCII code. And so that's being set into, so we're initializing our board to all blanks. And when we run it, well, let's not bother now. When we display the board, we're going to display these column headings, and then we'll display the values in the board. So I'm going to copy those lines. We'll have to do something like this. Looks like I've got 2 spaces, and then the value. Something like that, right? And then at the end of this inner loop, we need to do a line break. Something, I'm just kind of guessing right now. So we're going to try to drop that into column 3. We'll be done in a second here. You see how I'm building it up just slowly and just kind of figuring it out here? So when we read this player move, we need to change the state of the game. We need to modify the data that's stored inside the board array. So do something like this. So I'll say player turn, and we'll pass in the, you know what? I'm going to do this. We'll call that column. And I'll say, and we call the function player move. I'm going to pass in the column. But you know, what we'll need to do is we can do something like if illegal move, if column is an illegal move, then I'm going to do continue. That means go back to the top of the loop. I'll redisplay the board, ask to choose a column again. We could do more. We could report something. We can say, you know, that's not a good column. If a column is full, the player can't choose that column anymore. So we have to check for that. So I'll define a function called illegal move that'll return true if the move is illegal. Actually, yeah, that's all right. And otherwise, we'll call player move and tell that function player move to make the move. So it looks like we're going to need 2 more functions. We're just going to return false. And then we have player move. And we'll do nothing. Well, no. We'll implement that. Once again, you know, we're just going to try that stub, just make sure it works. All right, almost done here. So let's implement this player move. Remember, when player move is called, it must be the case we've already checked for an illegal move. We can use an assertion in there. Just to be extra sure. So that'll terminate for us. So we're assuming that, hey, whoever called us, see, we're sort of, at this point, we're sort of forgetting about what happened in main. In main is supposed to check for illegal move first before it calls us. So we could just assume that. That's the job of main. It's not our job. That's our decision as a designer, as a programmer. But just to make extra sure, let's just run a test. And we'll put it in this assertion here. That doesn't mean that main doesn't have to call it as well. We're just going to be extra defensive. Okay? So now, how do we move? Well, we got to find how do we do a move? What's the algorithm that we use? Like when it's my move, if I go here, oh, someone already lost the game. So if I go here, you know, what do I need to do in code for that? It's a loop, isn't it? I got to find the smallest index that has a blank in the given column. And that's where I put the X. So player will be X, you say computer will be O. So we want to find the smallest index in call that has a blank in it. We can use a for loop. And we're going to be actually ranging across the rows. So I'm going to use I there just to be consistent with the use of I in other parts of the program where I represents a row. So we'll start at 0. I is less than what? 6? If board of I call is blank, we found a blank. So we got to make our move, board of I call, then gets an X. And then what do we do? Anybody following? Nobody's following. What do I do right there? You see, I'm starting at the row 0 in column COL, and I'm scanning upwards to find a blank. Once I find a blank, when I gets big enough so that board I call is blank, then I found a place to put the player's X. So we write the X in that spot, and then what do we do?
Make it so you can't use that spot
We did that by putting an X there. So the next time we come in here, this will be false. So we're going to increment I, so we keep going up. Oh, you know what? We're going in the wrong direction here. Oh, no, it's the bottom. So is the bottom a 0? No, it's the top is a 0, right? So the top is a 0, so really,
It's for I's.
huh?
I is greater than 0.
I think we need to start,
Minus
I is greater than 0. I think we need to start, I mean, it depends how we want to organize it. That's right.
I equals 6, and then I is greater than 0, and you can do minus 5.
Yeah, it's I equals 6.
Here we go. That's better, isn't it?
Do we want to use 5 or do we want to use 6? 0.
I think we want to use 5.
Right, start with 0, back
Yeah.
to 1.
So, well, and I got greater than or equal to 0. That's good. As soon as I gets to be -1, we're out. So what do we do here? We return. We're done. Let's see. Is it going to work? It works. Well, the only problem, huh?
Except you entered 3 in and put it in.
Exactly. Because here, to the user, we're displaying 1 through 7. But internally, we're numbering them 0 through 8. So what I'm going to do, just temporarily, because we'll switch it back to make it better for the user. Well, I guess we could just subtract, right? We could subtract 1 here. We could do we could just convert to us like that, right? Whatever the user enters in, we'll just take 1 off. Does it still work? Well, look at that. Let's try 3 again. Look, is that great? You see how they build this now? We're doing it at one piece at a time. And we can finish this. We'll finish this before the end of the quarter in lecture. Okay. Anyway, that's it for today.
Quick question about the exam.
Yeah.
The exam is gonna have everything that's on your pack.
Yeah. Yeah, but the problems will look a little different, but it'll have that format.
Right, 'cause in the lab you included the insert function.
Yeah, that's